afternoon, good evening, or maybe even good night, because I have seen that there's a lot of people attending from everywhere. Welcome to this webinar, Social Networks for Fraud Analytics. The work that I will present in this webinar is partly my own work, partly the work of my PhD student Veronique van Vlasselaar, who will finish her PhD in October this year. I will start with a very brief introduction about myself. So my name is Bart Baasens. I studied at the KU Leuven, which is the best university in Belgium. Leuven is actually a very small city, definitely when you compare it internationally to American or some of the Asian cities. It's situated about 20 miles away from Brussels. It's well known for a couple of things. First, it has the best university of the country, but that I already mentioned, right? And next to having the best university, we also have lots of beers which are being brewed in Leuven. You might have encountered the beer called Stella Artois, which is a beer that is very popular outside Belgium. It's being brewed in Leuven, and if you look at the name tag on the bottle, it says actually also brewed in Leuven. The brewery is about, I think, 500 meters away from where I'm situated right now. So I'm situated at home, my window is open, and I can tell you at this very moment that I'm actually smelling the yeast of the brewery, which is a very nice sentiment to do a webinar. Anyway, I studied business engineer in management informatics at KU Leuven, finished that in 1998, and then continued to do a PhD. The title of my PhD was Developing Intelligent Systems for Credit Scoring Using Machine Learning Techniques. My PhD was finished in 2003, and afterwards I became a professor of big data and analytics at KU Leuven, where I'm still at right now. I'm also partly connected to the School of Management at the University of Southampton, where I also teach a course on credit scoring and data mining. My research is actually nicely summarized on my webpage dataminingapps.com, which recently underwent a serious makeover. So here you can see all the research that we are doing in marketing analytics, credit risk analytics, fraud analytics, process analytics, and human resource analytics. In this webinar, I'm going to zoom into fraud analytics and some of the approaches we developed there. By the way, we also have a newsletter. In case you want to subscribe, you can submit your email here. We send it out weekly. You will also find some videos here of some of the courses I've been teaching and some of the lectures that we have been doing on the topic of social networks, business process analytics, and so on. It's all for free. You can also find some books here that I recently wrote on the topic, right? And you can also see that the PhD theses of my PhD students are available here. You can actually download them. Here you can see my PhD thesis. I wouldn't say it's a very interesting piece of work, but if you want, you can download it there. Again, if you want to stay up to date, please feel free to subscribe to our newsletter by submitting your email address here. Great. Here you can see actually some of the background information of my PhD student, Veronique, who conducted the work together with me. You can find her contact details and more information about her work also on my dataminingapps.com website. Excellent. So what we're going to do today is I will quickly give you an overview of fraud. Then we're going to get into social network analytics. Then I will outline the gotcha fraud detection tool, which we have developed in my group together with Veronique, and which we have field tested already quite a number of times with firms. We will finish with some conclusions, and I will then also give you an overview of an e-learning course. Actually I have two e-learning courses, but I will give you a brief demo of one e-learning course entitled Advanced Analytics in a Big Data World, which I have developed together with SAS. Of course, there will also be opportunity for you to ask questions at the end of this webinar. Fraud. Well, fraud is a very important topic these days. You can see that fraud is present in many typical business processes. Think about credit card transactions. Think about somebody stealing your credit card credentials and making fraudulent purchases with your credit card. Think about insurance claim fraud. where somebody files a fraudulent insurance claim in order to recover money from the insurance firm in a fraudulent way. Think about opinion fraud. It is claimed that about 1/3 of the reviews which are provided online for sites such as Amazon, TripAdvisor, etc. are actually fraudulent. 1/3 is quite a bit. Social security fraud or closely related, tax evasion fraud. Scientific fraud. Think about plagiarism, which is actually a pest nowadays for many universities. So these are just a few examples of different ways of fraud. Now, fraud always refers to anomalous behavior, behavior that deviates from mainstream behavior. Well, before you can see whether behavior deviates from mainstream behavior, it is very important to both qualify and quantify the mainstream behavior. And this you can do at various levels. You can first do that at the data set level, where you're going to try to see whether the behavior of a person or an instance or a transaction does not comply with the general trend or the overall behavior. Think about the illegal setup of a customer account, and where a customer, for example, starts to heavily spend on his or her account in a fraudulent way. Here you can see a data set of observations, and you can see that the green observations are legitimate observations. These could be non-fraudulent customers, legitimate transactions, and so on. All of a sudden, you see this red transaction, which deviates in a certain way from the overall trend. Now, very important to be aware of is that it's not because there's a deviation from the overall trend that it is necessarily fraudulent. But at least it should raise a suspicion that warrants further investigation to see whether it actually involves a fraudulent or legitimate transaction or observation. So a first way that you can use in order to identify anomalous behavior is by analyzing behavior at the dataset level. But next to the dataset level, you can also try and qualify and quantify anomalous behavior at the data item level. Here you can see the behavior of a person or instance not complying with the normal behavior of that person or instance. Here you can see a series of transactions that were made at a specific date and time with a particular duration at a particular transaction location or origin. Now imagine that as the result of an identity theft, some of these transactions are not made by the customer but by the fraudster. These are the transactions which here have been labeled as bandit transactions. Somebody stole the credentials, think about credit card credentials, of a particular customer without that customer necessarily being aware of it. So all of a sudden, you see two types of transactions: the transactions of the customer, him or herself, which are legitimate transactions, and you now see them mixed with the transactions of the bandit, of the fraudster, who has stolen the credentials of the customer. So you can see, in order to define fraud, you can define it at the dataset level, or you can dig down the individual data item level in order to see whether there's any fraudulent patterns there. Obviously, this seriously complicates the fraud detection process. One of the key challenges with fraud detection is that a fraudster will try to stay unnoticed as long as possible. In other words, a fraudster will try to blend into its environment. It will try to hide him or himself as much as possible in order to not be noticed by fraud detection techniques. You can see this visualized here with this nice photo, which I embedded in my slide, of a frog which tries to blend into the environment. Well, this is actually what a fraudster will do as well. It will try to cover up its transactions, make it look as legitimate transactions, such that the fraudster will not get caught by fraud detection mechanisms. Obviously, this seriously complicates the problem for analytical techniques in order to detect fraud. If you look at the fraud cycle, and more specifically the fraud detection cycle, how it usually works is as follows. You start from an automated detection algorithm. And when I say an automated detection algorithm, this could be an algorithm or a technique which has been built using various underlying technologies. It could be based upon a set of business rules. Business rules are if-then rules based upon common sense, experience of a set of business experts. Think about insurance claim analysts or fraud analysts, and which have been written down into a rule base of if-then rules. Could also be a descriptive analytical technique based upon clustering or segmentation, based upon association rules, based upon trends analysis, or based upon breakpoint analysis. Or it could be a predictive analytical technique based upon logistic regression, based upon decision trees, or random forests. By the way, these are my three favorite predictive analytical techniques. So based upon an automated detection algorithm, you're going to try and detect fraud. As I already mentioned, when you detect fraud, you will label transactions, observations, or claims as suspicious. So this will necessitate a follow-up step in which the fraud will be investigated. Fraud investigation is something which always takes place in collaboration with the human expert, with the fraud expert. At the end of the day, it will be the fraud expert who will decide whether a transaction observation is fraudulent, yes or no. If the fraud is confirmed, then it can be fed again to the automated detection algorithm who can learn this new fraud pattern. So you have a continuous loop there of fraud detection, fraud investigation, fraud confirmation, and incremental learning by the automated detection algorithm. At the end of the day, the new fraud patterns should also be incorporated into appropriate fraud prevention mechanisms to prevent future fraud from taking place. So you can see it's a continuous cycle that you have to work in. And you see nowadays in the industry, and we collaborate currently with a lot of banks, credit card, and insurance providers on the topic of fraud detection, you see that analytics is getting more and more embedded into this whole cycle. How do we define fraud? Well, together with my PhD student, Veronique van Vlasselaar, we kind of came up with a definition of fraud. We do not want to claim that this is the best definition of fraud, but it's at least a definition which we think is very useful to develop our analytical approaches for fraud detection. We have qualified fraud as an uncommon, well-considered, imperceptibly concealed, time-evolving, and often carefully organized crime which appears in many types and forms. Fraud is uncommon. That means that in the data sets that we tackle, usually we have less than 1% of the claims or observations that are fraudulent. This poses some serious problems for analytical techniques such as logistic regression, decision trees, and so on. Fraud is well considered. That means it's intentional. It's with malicious intent. It's imperceptibly concealed. That's the idea already mentioned earlier. A fraudster tries to blend into the environment as good as possible to hide his or her fraud tactics. It's time evolving. As soon as the analytical technique is being used for fraud detection, the fraudsters will try to beat it by coming up with new fraud mechanisms. That means that you have to continuously monitor, backtest your analytical technique in order to make sure that you keep up with the new fraud mechanisms. It's carefully organized. I can already tell you that according to the studies that we have done with some firms in the industry, fraud is very social. That means that you typically have lots of fraudsters that collaborate, set up collusion practices, develop fraud rings, and so on. So based upon this definition, we can now start doing analytics. And if you want to do analytics, you have to first understand the business problem. I've written this in two of my books on the topic of analytics and fraud analytics, that one of the key things that you should do as you start doing analytics is understand the business problem first. If you understand the business problem, you can start thinking about analytical approaches in order to solve it. Those analytical approaches should preferably have some characteristics like accuracy. Accuracy, as it's measured by precision and recall. Precision says how many of the labeled transactions, the transactions that are labeled by our fraudulent technique, how many of the transactions that are labeled by our analytical technique as fraudulent, how many of those are actually fraudulent. Recall says how many of the known fraudulent transactions are labeled by our analytical technique as fraudulent. Besides that, you can also look at the AUC, which is the area under the ROC curve, which is a key performance diagnostic for analytical fraud models. Besides that, you also have to take into account operational efficiency. We have developed, together with a major European credit card provider, an analytical technique to tackle credit card fraud. Now, the analytical technique for that particular credit card provider had the 6-second rule. In order to label a transaction, a credit card transaction, as fraudulent, yes or no, we had 6 seconds after the transaction was initiated. That means that we have to take into account this operational efficiency requirement in the development of our analytical technique. And that was not that easy. Of course, we should also take into account the economical cost. What is the cost that is needed to set up, develop, estimate, build, but also monitor the analytical model? All those costs should be taken into account. And as I've recently written in one of my blog articles, it's usually very easy to determine the total cost of ownership of an analytical model by looking at the acquisition cost, by looking at the production cost and the post-acquisition cost, but it's a lot harder to quantify the ROI, or return on investment, of your analytical fraud model. Finally, analytical fraud models should be interpretable. Why should they be interpretable? Well, that's very easy. If you look back at my previous slide, at the end of the day, you want to do fraud prevention. You can only do fraud prevention if you understand the fraud, right? So that means that techniques like neural networks or random forest, although they can be very high performing in terms of AUC, precision, and recall, you should be very careful with them because their interpretability is a main weakness. In our research, we have developed some approaches in order to make these black box approaches more interpretable. Okay, when I say social network analytics, many of you will undoubtedly think about Facebook, Twitter, LinkedIn, and so on. Obviously, to me, these are very important social networks, but I prefer to refer to those as social media. When I say social networks, I'm referring to any network of entities linked in a particular way. Those could be companies linked by means of shared manager, shared employees, shared accountant, shared physical address, shared equipment. Those could be credit cards and merchants linked by means of transactions. It could be web pages or websites linked by means of hyperlinks and so on. So to me, a social network is more than just Facebook, Twitter, and LinkedIn. I've actually recently had some discussions with the UK Tax Inspection Service and some of the other tax inspection services worldwide to understand to what extent data from Facebook, Twitter, or LinkedIn can be used for fraud detection. And at this stage, I must be honest with you, I still haven't got any clear answer on that. So to me, it's still unclear to what extent Facebook data, Twitter data, even if it's publicly posted, can be used for fraud detection without violating a customer's privacy. As I already mentioned, social networks are more than just Facebook and Twitter. Here you can see a dump from a real-life social network that we got from a major European credit card provider. I'm not going to go through all the nodes. You can just see that the blue nodes are merchants. The red nodes, or actually the rectangular nodes, rectangular shaped nodes, are credit cards, and the links represent transactions made by a credit card at a particular merchant. You can see that some of the links are colored green. These are legitimate transactions, whereas some of the other links are colored red, which are the fraudulent transactions. when you look at this graph, if you just inspect this graph, you can see a lot of clustering going on here. You can actually see a community of credit cards and merchants with a lot of red connections. This clearly indicates already a social network effect. The first way to see whether there's a social network effect in your data is visualization. Remember, when you do statistics, descriptive statistics is always very important. Well, just looking at your graph and visualizing certain portions of it, here in this particular case, by looking at certain communities, can already give you an indication on whether the phenomenon that you're studying is social, yes or no. Here you can clearly see this. We also collaborated with and actually we're still collaborating with the Belgian government to detect tax evasion or social security fraud. This concerns companies that intentionally do not pay their social security taxes. Here you can again see a dump from the network that we have been working with, and again you can see a clustering of red dots here representing fraudulent companies that do not pay their social security taxes. So by merely inspecting a social network, you can already have like a common sense feeling of whether the phenomenon that you're studying is social, whether there's any social network effects, yes or no. To zoom into the social network, or more specifically the social security fraud, I'm going to outline one mechanism which is sometimes used by companies to engage into tax evasion activities. So here you can see a key company which is the key perpetrator of the fraud. And what it does is it takes some of its resources and brings it into a site company one. Resources, when I say resources, I'm thinking about some of its employees, some of its equipment, some of its physical infrastructure, etc. The site company one is intentionally not going to pay its government taxes or social security benefits. It's not going to pay those. So it intentionally goes bankrupt. Actually, when it goes bankrupt, this is not a true bankrupt, but it's a fraudulent bankrupt. And as soon as it went bankrupt, the key company is going to take all the resources of that site company and put it into a new site company too. It will again do some business, it will again gain some revenue, but again, it will not pay its social security taxes or governmental taxes and go bankrupt. Once the bankruptcy event has taken place, the key company will again move all the resources, start up a new company, and so on. This is what we call a spider construction. And based upon our collaboration with the Social Security Inspection Service of the Belgian government, we were being informed that these spider constructions are a frequently adopted fraudulent mechanism by companies that engage into fraudulent activities in Belgium. So we started defining our network. We started defining the nodes in the network, which are very obviously companies, and the links. I cannot tell you how the links have been provided or have been defined because that's part of the secret. If I would tell you that, fraudsters would know how we would track them and they would start develop new mechanisms. But I can tell you that the links have been defined based upon shared resources. However you want to qualify a shared resource, like a shared CEO, shared board members, shared employees, shared infrastructure, etc. In order to tackle this, we developed our gotcha fraud detection tool. The gotcha fraud detection tool makes use of various types of data sources. First of all, social networks are interesting, but they are not magic. So it's very important to level set your expectations in the right way. Do not anticipate too much performance benefits. Social networks usually provide you with a nice add-on. So actually, when you think of that more closely, if this network represents firms, what we will now do is we will first take into account the local characteristics, the firm-specific characteristics based upon the profit and loss statement, based upon balance sheet information, and so on. You first look at the non-network characteristics. We sometimes call these local characteristics or intrinsic characteristics, local attributes. Besides that, we're also going to take into account the network. And we're going to quantify the network by featurizing it. Featurizing means that you build data characteristics which you're going to feed to your analytical technique by analyzing the network. And we're going to build direct network attributes as well as indirect network attributes. I'm going to explain that later in a moment. So we take various sources of data to construct our local company-specific attributes, or direct network attributes, and our indirect network attributes. This is based upon factual data, historical data, and transactional data. That will then be offered to a learning algorithm. In our particular case, that will be logistic regression or random forest. The model that comes out will be a fraud detection model that can then be used to label data, label transactions as fraudulent, yes or no. This is our whole gotcha analysis tool. And we actually wrote some papers on it, which I cannot share with you at this very moment because they're still on the submission, but they should be available in the next 3 or 4 months. We also plan to make our gotcha tool, which has been now field tested with 2 firms and has been developed in R, available on our dataminingapps.com website. So very important is that we try to provide the right balance between intrinsic and network-related features. As such, gotcha tries to address all the challenges that we outlined earlier when we defined fraud. We try to take into account the interrelationships between instances, claims, and so on by inspecting the network and by quantifying it into direct network attributes, of which I will give you some examples soon, and some indirect network attributes. Time evolving is also taken care of because our goal gotcha analytical technique will be complemented with monitoring and backtesting techniques to continuously monitor whether it still performs well. We try to take into account as much information as possible. More specifically, we try to take into account all information available, such that even when it's imperceptibly concealed, we can give it our best shot to detect fraud. Well considered? Well, we take all information into account. In our gotcha approach, we also have a very particular procedure, which I cannot comment on because of time constraints, but it's the smoothie procedure, which has been embedded into our gotcha approach to deal with the fact that fraud is very uncommon and that analytical techniques such as logistic regression, decision trees, and random forest can be blinded or can be freaking out on all the non-fraudulent transactions, because if you only have 1% fraudulent transaction and if your decision tree says every transaction is non-fraudulent, then obviously it will achieve a classification accuracy of 99%, which is not what we want. We have applied this in 2 applications: social security fraud, whereby we try to detect those fraudulent spider constructions that are already referred to before, and in credit card transaction fraud. A key challenge in both of these settings is always to define a network, and not only to define a network, but defining the network in such a way that it clearly tells us something about the fraud mechanisms which are being used by fraudsters. So again, remember, we start from the data sources, then we move on to network analysis. We featureize it, so we derive features or characteristics from the network, both direct and indirect features. We add that to our data, which is now our network database. We then provide that to a learning algorithm, and that's how we developed our gotcha approach. In terms of data sources, we make use of various underlying data sources. Factual data. Factual data is going to give us the intrinsic firm-specific data characterizing the current state of the observation or firm. Think about the sector in which the firm operates. In some sectors, you see more fraud than in other sectors. Age of the firm, financial statements data, balance sheet data, and so on. In a credit card setting, this could be the demographics that comes with the card holder, bank statements, etc. Historical data looks at changes in the instance behavior, changes in a company's state, changes in legal form sector, changes in demographics, and so on. This could be also a very useful indicator for fraud. And finally, we have transactional data. Transactional data will look at interactions between companies, interactions between credit card holders and merchants. it is exactly the transactional data that will typically allow us to build the network and then to start featurizing it. Transactional data is typically the add-on on top of the factual data and historical data that proves to be very interesting. So again, the network representation is important, and it's important to carefully design that network, taking into account all underlying data. And this is something that you as a data scientist will not do in isolation. You will do it in collaboration with the business. The business expert, the fraud experts, are going to give us very useful starting insights about existing fraud patterns that can help us steer the development of our network. Remember the spider construction. When we started working with the Belgian government, we were not aware of the spider construction mechanism. So this was a mechanism which we kind of figured out by talking to the guys of the government. And then we started defining how the nodes, which were the companies, and the resources. And this was really in very close collaboration with the business expert, the fraud analyst. Now, the weights also were, the links were also weighted. The edges are also weighted. Obviously, when two companies are connected and they're both fraudulent, but the connection dates back to quite a while ago, then this is less important than a connection which is still actual at this very moment, and it happens to be fraudulent as well. So we try to assign weights by taking into account the time information. I told you fraud is time evolving, right? So we take into account a time-weighted link in this way into our network. Obviously, I cannot comment on how time has been incorporated exactly, but we have incorporated a time-based weighting mechanism into our network as well. Furthermore, when you build a network, it's very important that you can take into account different types of networks. When we started doing our research, we worked on unipartite networks, and a unipartite network is a network in which you only have one type of nodes. Think about the Social Security example where we only had firms. A firm is one type of node. We could extend that to a bipartite network in which we not only look at firms but also at resources. However we qualify a resource, be it an employee, be it a shared address, and so on. So by considering two types of nodes in the network and the links between, your network is being enriched. This is a type of data enrichment that you're doing, and which will also be to the benefit of your fraud detection model. Right now, in our credit card transaction setting, we're working with multipartite graphs in which we have three types of nodes: credit cards, credit card holders, and merchants. And that proves to be very beneficial to our credit card detection technique. So the network should be built in such a way that it actually achieves the ultimate goal. And the goal here is fraud detection. Also, our network should be scalable, especially from an operational efficiency perspective. Remember the 6-second rule, in which I said you should be able to detect credit card fraud in 6 seconds. So that means that your network should be equipped with incremental facilities to adjust to new fraud patterns, to adjust to new nodes, new links, etc. One of the mechanisms that we use to also analyze networks from a fraud perspective is the Google PageRank. Google has a PageRank algorithm that decides upon how to rank order pages in terms of their relevance. We programmed the Google PageRank algorithm, embedded it into our gotcha technique, and started seeing how fraud spreads through the network, much like a virus. How the influence of a fraudulent node, here you can see a multipartite graph. You see the circles are companies and the diamonds are, resources. And if you have a fraudulent company, it's going to spread its influence through its resources, employees, shared board members, whatever. And those resources will then spread it further to their connecting companies. Now, we have successfully modeled this mechanism based on the Google PageRank algorithm. In a Google setting, the nodes would be web pages, and they would spread their influence to linking web pages, other web pages that they link with. Well, we have adjusted the Google PageRank algorithm to a fraud setting in order to spread fraud influences throughout a network of interconnected nodes. Actually, by doing so, we found that our algorithm has an anticipating and a forgiving effect. Anticipating means that if you would have, for example, a firm which has 0 fraudulent resources, but because of the structure of the network has lots of incoming bad influences, we will anticipate that this firm might be engaged into fraudulent activities in the near future, right? Because it has a lot of incoming fraud influences. Vice versa, we also have a forgiving effect in the sense that if you would have a company which has been engaged into fraudulent activities in the past, but it has a lot of good incoming influences from legitimate or non-fraudulent firms, then we tend to forgive the fact that the firm has made a fraudulent mistake in the past. This is all nicely incorporated into our algorithm. As I said, we also mentioned that it's very important to mix the network features with intrinsic features, local features, as if the entity, as if the credit card, as if the firm was treated in isolation. And here, as I said, you can look at demographic data such as sector, age, financial statements in a social security setting, or in a credit card setting, you can look at the RFM variables. RFM is a set of marketing variables which have been popularized by a guy called Cullinan in 1977, and which is often used for marketing segmentation, churn prediction, response modeling, but which have also been successfully used as intrinsic or local variables for credit card fraud detection. R refers to the recency of the transaction, F refers to the frequency of the transaction, and M refers to the monetary value of the transaction. We've used that as well. So we combine that with the direct network features and indirect network features. Direct network features are features that we immediately get from the direct neighborhood. An example of a direct network feature is how many fraudulent resources is a company connected to. That's a feature that comes from the direct neighborhood of that one particular company. The direct neighborhood, in other words, a company and its immediately surrounding resources, or what we call the egonet. It's like Bart and his immediate friends. If you look at Bart and his immediate friends, that's my egonet. And that's an assumption that we work with in our approach to make it scalable, right? Because obviously I could also look at the friends of the friends, but that might be interesting from a performance perspective, but believe me, those things are really hard to scale in a real-life fraud detection environment. That's why we only look at the immediate neighborhood at the resources a particular company is connected to. Here you can see some further examples of direct features. For example, in a credit card transaction setting, we can look at whether a transaction is connected or to a fraudulent merchant, yes or no, or vice versa, the number of fraudulent transactions connected to a merchant. So we only look at the egonet, at the one-step links. We only look at the immediate environment of each individual node to facilitate the whole analysis. Our indirect network features then come through the application of our PageRank technique. PageRank is like a collective inference algorithm, and it's going to spread fraud influence through the network, and it's going to actually successfully try to model those anticipating and forgiving effects that we have briefly referred to earlier. We have successfully applied this in social security fraud. Here you can see some of the ROC curves. I'm not going to comment on them. These are out of time validations, as I think it should be validated, on the short term, medium term, and long term. I'm going to tell you that the main finding we got here is that fraud in this particular setting is a social phenomenon. We found that social network effects significantly add to the performance of traditional predictive analytical models built using only local characteristics, firm-specific characteristics. Actually, some of the bankrupt firms that were labeled by our technique as fraudulent were very suspicious, and we thought that some of those bankrupt firms, despite the fact that they were labeled as bankrupt firms, were actually fraudulent firms instead of bankrupt firms. The same finding we got in credit card fraud. We were absolutely flabbergasted by the amazing performance we got there to detect fraud. Our AUCs ranged around 95%. The first time Veronique presented those findings, I was very skeptical, and I asked her to validate those again, because I've hardly seen analytical models that reach up to 95% of area under the ROC curve. So she validated again. She validated in collaboration with a Chilean researcher that we often collaborate with, and she validated on out of time data together with the firm we've collaborated with, and it was just the fact that the ROC was that high. And we saw that network variables really played a very important role in credit card fraud detection. We're currently also testing or expanding our gotcha approach to also work in other settings like in insurance claim fraud detection. This was in a nutshell some of the work that we've been doing. I realize that there's a lot more to talk about, but I only have a limited time frame available. So I'm going to give you some pointers to further information about this. First, there are some of the books that I've been publishing lately. This is a book which I published, Analytics in a Big Data World, 1 year ago. We sold about 3,500 copies right now. There's a very small part on fraud detection in it. You can buy it on Amazon if you're interested. This is a new book which I co-authored together with Veronique and Wouter Verbeke, a colleague professor working in Brussels, and it focuses on fraud analytics. It will be available from August onwards, but you can already see the table of content on Amazon. I also teach a couple of courses together with SAS. Despite the fact that the courses are offered together with SAS, they do not focus on the SAS software. We focus on the modeling concept. So I have a credit risk modeling course. It's a 4-day course. At this very moment, a colleague of mine is teaching it in Marlow in London. It focuses on credit risk modeling, validation, and development. It's a 3 or 4 day course. Analytics, putting it all to work, is a 1-day course. Advanced Analytics in a Big Data World is a 3-day course. Web Analytics and Web Intelligence, this course is getting a little bit outdated. It is a 2-day course in case you're interested. And I have one on fraud analytics using predictive, descriptive, or supervised, unsupervised, and social network learning. These are all classroom courses, but the good news is I also have courses which are developed in e-learning format. And here you can see my Advanced Analytics in a Big Data World course. I will briefly give you a demo of that course. It's only a 2 to 3 minute demo. It's an e-learning course which is offered in collaboration with SAS. And again, it does not focus on the software, rather it focuses on the concepts and the methodology. So it's a course, it's not available for free because we spent quite some time developing it, but upon registration, you will get a link here where the course will be listed in your e-learning portfolio. So I will click Advanced Analytics in a Big Data World. Then you get a start screen, which looks like this, and then you can start the course. It's about 20 hours of movies. 20 hours of movies which have been pre-recorded and which you can play as many times as you want during 1 year or 350 days, right? Let's have a look. Here you can see the outline of the course, right? It has 8 lessons. The analytics process model, decision trees, ensemble methods like random forest, boosting, bagging, neural networks, support vector machines, Bayesian networks, survival analysis, social networks, and monitoring analytical models. In the context of this presentation, I believe social networks is the most important lesson. So this is a set of videos, right, which discusses the topic. So you can see that we have a lot more input on social networks for fraud detection. I'm going to play it, so the video comes with audio. You will not hear the audio because I'm now using my audio to talk to you, right? So it's interfering with that. All movies have been subtitled. You can also get the text accompanying, the script accompanying each movie, in case you want to read it. We have various movies, all about 3 to 4 minutes, right? So we have the movies on the PageRank algorithm. Here you're going to get more information on the PageRank, and how that can be used for fraud detection, for example. So it actually explains, together with some examples of how you can use that for fraud detection. Of course, we also outline our gotcha fraud detection method, and we do that into a lot more detail than I did in this very brief presentation. Right, so this is our gotcha fraud detection. The course also has questions to every now and then see whether you understood what is being said, right? And it has feedback as well. Every lesson ends with a quiz, which has about 10 questions, right? And to see whether you got the material. You can take the quiz as many times as you want. And at the end of the course, you're also going to get a certificate. So there's a course certificate that you can also print out. Now, the course also comes with SaaS demos in base SaaS, in SaaS Enterprise Minor, but this is not the main focus of the course. So if you go to decision trees, you're going to get, if you look at creating decision trees, here you're going to get an example of creating decision trees in Enterprise Minor. But even if you're using other software, I mean, it doesn't matter because the course focuses on the theoretical aspects. Also, well, actually, if you'd be interested in this, I can give you more information, or you can click on the link in this slide. Also, to finish, I'm more than happy to refer you again to our data mining apps website. As I said, it recently underwent a serious makeover. We have lots of partnerships and research shares which we engage in together with firms. You can see them all listed. There's lots of free material, like free videos on it. There's lots of some PhD text that you can download, and you can subscribe to our newsletter. Okay, so this finishes everything I wanted to say.